So now in this video we're going to look at a couple of integrated circuits here. They're for the most part the same integrated circuit, so they're the quad 2 input positive NAND gates. One of them though is from this kit there. It was right there. So SN74HC00N. So the SN part's not really important, neither is the N. We have the 7400 series integrated circuit. As you can see, these two are both say 74, and so that one's 00, that one's 02. So 00 lets us know it is a quad 2 input positive NAND gate. Now the HC part of it, that lets us know that it's a high speed CMOS integrated circuit, and that is what I'm used to using for the most part. The kit here, I have the 74LS00. So again, it's the same circuitry, but it is a low power schottky version. And so I just got this kit recently. As I said before, I'm used to using the high speed CMOS, not so much the low power schottky. And the video I made, I think it was my last video, I used the 74LS14. I do not have the HC version of the F14. I ordered a new kit though that does have it, so probably next video we will look at that. But in any case, let's get to it. So we're using the bottom NAND gate, and if it was an AND gate, the AND gate's just easier to understand, so let's get to that. For a high output, you can see the output's high, the LED is on, but for an AND gate you need a high input and a high input. Two high inputs is the only way to get a high output for the AND gate. The NAND gate is the opposite. You need a high input and a high input, so both still high inputs to get a low output. Otherwise, the output's high. As you can see there, we have two lows and the output is high. Let's move that, see if that makes it a little easier to see what's going on. We move this one over to the positive rail, and you can see, so that's a high signal, 5 volts. These integrated circuits, it's best to use 5 volts. Of course, always look at the data sheet for exact voltages if you want to make adjustments. But there you can see we got a little bit going on. But for the most part, the output did not go low until we had a solid high signal at both of the inputs right there. And so one of them floating, it does not sink low. So this is the high-speed CMOS version, the HC version. Now, what we're going to do is just kind of quickly slide this over and do a visual comparison again. And plus, remember, you have to power these integrated circuits. So we got VCC jumper there, top pin to the left, and then ground. We have a gray jumper over there. So I'll just remind you of that before I forget. So I'm using 5 volts. You should use 5 volts, but you can consult the data sheet for different voltages. It can go a little higher or lower. But in any case, this is the LS version from that kit that I showed you. But otherwise, it's the same circuits. It's quad. There's 4 of them, NAND gates. And it's going at an angle. These integrated circuits also, the data sheet will probably tell you not to touch it, because if I shock it with electrostatic discharge from my body, I may fry it. But it costs about 50 cents to buy a new one, so I don't care. And I wouldn't need to get things done quick. So there we go. Again, both inputs have to be high for the output to be low. That is the main thing for the NAND. And so we're going to yank this one up here and put it to the positive rail. So far so good. The output's been staying high. We haven't had both inputs high yet. But when I yank that one, now you see the LED goes out. So these inputs behave differently a little bit, you know, not horribly. If we give it a solid positive connection, well, the output is out still, you know. But we saw with this is the low power schottky, we saw with the high speed CMOS, the HC, that when we had one floating, the output was high as long as, well, if one of them was floating, the output was high. The only time it went low is if we had a definite high signal at each input. Then the output went low. But here you can see we don't have that. But if we go negative, then we do have it. So this is right. So as long as you have an absolutely sure high or low signal, they both operate exactly the same from what I've seen, you know, as far as the output is concerned. So let us take the oscilloscope now and actually look at the waveforms. And so I really love this oscilloscope. It costs about $42, and so obviously it's not the best oscilloscope in the world. If you were taking a class or something, you'd probably have to buy a better one, I'm guessing. And but for what I do, this works just fine. So the black, I call them probes, but they're alligator clips. Black alligator clip from that cable. I have a clip to another alligator clip. I'm going to put that to the negative rail. And we're just going to look at one of the inputs and maybe later the output. So we put that to ground, and then the red one we'll put to the lower input right above the output. And the resistor is to the positive rail. That's no surprise that we have a high output. Let's move this resistor to the positive. And there you can see we had it floating and it was off. So that's one thing to take away. Now we got the resistor to the positive rail. We expect that we would have the 5 volts. Now as soon as I plucked it, you saw it quickly dropped, and it's a little bit more than 1 volt. It's 1 volt per square. While it is floating, it's really steady. It's not going chaotic or anything. So that is the most interesting part. Now we give it 0 volts, so we do have a definitely low signal, and since at least one of the inputs has a low signal, the output is high. That's the main takeaway right there. So let us leave it as we have it now. We'll turn the power supply off, and we will look at the HC version, the high speed CMOS one, and we'll put it there. So there's a little divot at the top. There's also a little dot there, but we got a divot up here. That's how we know that's where the top is. Now we turn the power on, and so we do not have a high signal at both pins, and so the output is high as we expected. So we have low, and you can see 0 volts there. First let's put this one high right there. Okay, so high at one, low at the other. Now let's leave this one floating, and there you can see that is what we commonly see with floating pins, a lot of noise, and there is a pattern to it. Let's go to seconds per division, and we will speed it up, and it goes to the purple one once it goes fast enough. So what do I got to do here? Go to that one, hit this to speed things up. They put some arrows there, and we go up there. So that looks like that is the waveform that we are dealing with. I don't know why once we speed it up it goes to this purple one, but in any case, let's go back to 1 second. Get that so it goes down. We have it set so it goes faster. Right there. So yeah, you can see it's just chaotic right there. And let's look at the output. I'm sure the output, so it looks like it's steadily on, but some of those spikes look high enough, and I don't know. Yeah, it looks like if I touch that resistor, we might get some spikes. But in any case, let's look at the output. So there you can see it's high, and we kind of, looks like we disturbed it, and we got a bunch of low spikes. So that would be when we get high enough spikes from the floating input, apparently. So in any case, let's go back to the input, and there you can see it's chaotic. So with the low power Schottky one, when the pin was floating, it just went to a solid 1 volt, and apparently that is part of the high speed part of it, and so it helps bounce it to the other rail if it's going from one extreme to the other. And so there's more information online about that. But in any case, this particular circuit doesn't really matter too much which one I use. So I could have made this with the high speed schottky one, or the high-speed CMOS one, or I could have made it with the low-power schottky one, and it would work pretty much the same. I didn't have a problem. The problem I had was in my last video with the 74LS14, which is an inverter. So when you give it a high signal, the output's low. It's only got one input. And if you give it a low input, the output's high. So the output's the opposite of the input, but there's a schottky part to it. So it's not one definite point. If you go down low enough, then the output goes high. Then you gotta go up a bit before it will set the output low. And I was going to use a capacitor to bounce that back and forth. It did not work as well with the low power schottky as it should work with the high speed CMOS. So we'll probably look at that in the next video. I think that'll be a better comparison, but still, hope you enjoyed this video. Thanks for watching. I'll see you in the next one.